Alright, so in this particular situation, we want to find the four electrostatic quantities at point A right here, and we will go ahead and put an actual charge here, and we'll say that it's positive, and that it is, let's say, 8 microcoulombs. Alright, so the first thing that we want to do is convert everything into base units so that we can work with them a little bit easier. This is going to be a negative 22 e to the negative 6 coulombs. This is going to be 18 e to the negative 3 meters. This will be 5 e to the negative 3 meters. And this will be 16 e to the negative 6 coulombs. And this one will be 8 e to the negative 6 coulombs. Okay, and then we are looking for the electric force, the electric field, the potential energy, and the voltage here. Since there is an actual charge at A, we will have force and a potential energy. The first thing that we want to do is probably calculate the voltage at position A due to each of these other charges. So the formula for voltage is kQ over R, and we want to know what is the voltage at A due to this charge. So this will become Q1, the Q that we're plugging into our formula. So let's go ahead and pull up our calculator. Nope. Alright, so K is 9 e to the 9. Our Q is negative 22 e to the negative 6. And we will divide that by the distance, which is 18 e to the negative 3. And we get negative 1.1 times 10 to the 1, 2, 3, 4, 5, 6, 7. So negative 1.1 e to the 7 joules per coulomb. Notice that our voltage is negative because our charge was negative there. And then to do the voltage for the second one, do Coulomb's constant, K times our second charge, which was 16 e to the negative 6, divided by R, which was 5 millimeters. And we get 2.88 e to the 1, 2, 3, 4, 5, 6, 7. So 2.88 e to the 7 joules per coulomb. Now, since voltage is a scalar, we can actually find our total voltage by just adding these up. So negative 1.1 e to the 7th plus 2.88 e to the 7th. And we get 1.78 e to the 7th. 1, 2, 3, 4, 5, 6, 7. So 1.78 e to the 7th joules per coulomb. So we found our voltage. Now we can find our potential energy by taking our voltage here, which is in joules per coulomb, and multiplying it by the charge that we have here at position A. So we can go ahead and say, alright, this 1.78 e to the 7 times the coulombs we're given, which was 8 e to the negative 6. Alright, so we have 142.4 joules. Alright, And then we could find our electric field, so let's go ahead and do that now. Electric field is kq over r squared, so let's go ahead and find it for point A due to this Coulomb charge, the negative 22 first. So we've got 9e to the 9th times 22e to the negative 6, and we use the absolute value of that 22 microcoulomb charge with our electric field over the distance squared, so 18e to the negative 3rd squared. And we get 6.1 e to the 1, 2, 3, 4, 5, 6, 7, 8 newtons per coulomb. And we want to go ahead and find the direction here. Now between these two particles, they're going to attract each other, so they're going to pull. This one is going to pull up on this positive charge. So our electric field will be 6.1 e to the 8th up. This one is actually going to push our positive particle to the right, and we want to figure out the magnitude for that. So we will say K times Q, which was 16, over R, which was 5 millimeters, squared. And we get 5.76, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5.76 e to the 9th newtons per coulomb to the right. Now notice that this 16 microcoulomb charge is smaller as far as the absolute value is concerned than the 22 microcoulomb charge, but that the electric field is much greater because this distance is much smaller. So essentially what we have is an electric field going to the right with 5.76 e to the 9th newtons per coulomb, and going up 6.1 e to the 8th newtons per coulomb. So to find our net electric field, we're going to use the Pythagorean theorem. So 5.76 squared, or e to the 9th squared, plus 6.1 e to the 8th squared. Okay, we're going to take that number, I'm going to store it as x, and then take the square root of x. Alright, and we get 5.8 e to the 1, 2, 3, 4, 5, 6, 7, 8, 9. So 5.8 e to the 9th newtons per coulomb. But electric field is very special. It's a vector, so it has magnitude and direction. So we need to go ahead and figure out what the direction is here. We always do inverse tangent of y over x. The first thing that we want to do is make sure we are in degree mode. And then we will say inverse tangent of y, which was 6.1 e to the 8th, over x, which is 5.76 e to the 9th. And we get 6 degrees. And we were expecting something in the first quadrant, and this is in the first quadrant, so should work out. Now notice that our x is much, much, much greater than our y, which would cause the angle to be pretty low there. So our electric field is 5.8 e to the 9th newtons per coulomb at 6 degrees. And then to find our electric force, we now have an electric field in newtons per coulomb. Well, we are concerning ourselves with this 8 microcoulomb charge. So we can take 5.8 e to the 9th newtons per coulomb, multiply it by 8 e to the negative 6 coulombs, and the coulombs will cancel out, and we'll be left with our force. So 5.8 e to the 9th times 8e to the negative 6, and we're given our force, which is 46,400 newtons. And it's going to have the same direction as the electric field, because remember, electric field lines always move the way a positive particle would feel a force, and we are talking about a positive particle.